So welcome everyone. Thank you for making it today on a very busy day and in a very busy last week of classes. This is the last climate science seminar from the YCI for this semester. We have 4 additional ones in the spring, but the last one for this semester, and we're very happy to have Jon Egill Kristjansson here today from University of Oslo. He is currently on sabbatical at NCAR, so he had a shorter travel than he would have otherwise. Jon Egill got his PhD from the University of Bergen, an excellent place to study meteorology, as many of you will know. Afterwards, he worked at the Norwegian Met Office for a little while, then went to do a postdoc at Los Alamos National Lab, and then after that, he took a faculty position at University of Oslo and has been there since for 21 years, he just told me. Jon Egill also was my PhD advisor and has been a tremendous mentor to me for more than a decade now, actually. So I'm very happy to have him here today. He's going to talk to us about climate engineering and how climate engineering could influence the hydrological cycle. He's had both EU funding and Norwegian funding to do work on geoengineering, and that's quite rare. There's not much funding for that kind of work right now. So we'll hear about some of that today, and Jon Egill, take it away.
Thank you, Trude. It's really good to be here and good to see you again. I've been very fortunate to have some good students through the years, and Trude is a prime example of that. And it's my first time here at Yale. And the topic today, I mean, I've worked on many topics over the years, and I got into this through my interest in aerosol cloud interactions. Climate engineering, of course, is a very complicated topic in a lot of ways, and has many political aspects and philosophical, moral aspects. So I'm happy to discuss that with you, but the main focus of my talk will be on the natural science aspects of this, but I will also touch on some of those other disciplines that are involved. And in fact, the U-Trace project, which has this logo there at the top, was just ended a couple of days ago. In fact, it's an EU-funded project, and that is a European transdisciplinary assessment of climate engineering. So that's a very broad project in terms of disciplines. And that's really required in order to deal with a topic like this, because it involves so many aspects from governance to moral issues, and of course technology and natural science. Okay, but today I will so I will give you an overview of climate engineering and research on that, and then I will narrow it down a little bit to have a special attention or focus on the hydrological cycle, which I think in many ways is the most important aspect of climate change in general, that I think humans can adapt to changes in temperature to a significant extent, but big changes in the availability of moisture, I think, are much more challenging to people. And that's why I think it's a key question whether we talk about global warming or climate engineering. And I'd like to acknowledge my co-authors, Helene Muri, who's with me in Oslo as a postdoc, and Hauke Schmidt in Hamburg, whom I've collaborated with, and who also led the IMPLIC project. Okay, so why are we sitting here or standing here now talking about climate engineering? I guess you all know why this has been coming up over the last few years with growing interest. And one way of thinking about that is through this figure I got from a colleague in Oslo at Cicero. And what this figure shows is what it would take in terms of emissions to meet the 2-degree target. And of course there are many ways to calculate this, and you may get slightly different results based on how you do that. But I think qualitatively speaking, I think these are sort of state-of-the-art results we're seeing here. And the point being that this here's the temperature change based on sort of typical climate sensitivity assumptions. So if you want to end up around 2 degrees at the end of the century, you really need to bring the emissions down to these colored lines here. And this would mean this kind of evolution of global CO2 emissions and this kind of evolution of the CO2 concentration. Alternatively, if we follow these gray lines, which maybe might look a little bit more realistic, I don't know, hopefully not, well, then we're not at 2 degrees, then we're getting close to 4 degrees. So it just gives an idea of what a challenge it is to really meet the 2-degree target. Of course, you could say, well, it's an arbitrary target, and maybe it is, but still it gives an idea of, 2 degrees globally is something like 5 or 6 degrees in the Arctic. So it is a very dramatic change. So the question is, okay, if it's that hard and we're still on a business as usual pathway, is this really going to happen? Are we going to do this? And I certainly hope we will, but at least it's enough background to motivate that maybe we should at least know what climate engineering is and whether it really is an option and how it might work if we were ever to consider using it. And the scientific motivation for believing that it might work is that we have these natural experiments, climate engineering experiments every now and then when our planet decides to spew out huge amounts of SO2 into the stratosphere and cool down the Earth's climate. And this, of course, has happened several times over the Earth's history to a varying degree. The latest and best documented of these eruptions was the Pinatubo eruption in 1991, which cooled down the Earth's climate by about 0.5 degree. Of course, it's only a temporary cooling because the residence time is about 2 years of these particles. But still, it's a very consistent signal that we see for all these major eruptions. So the question, could we deliberately inject particles like this into the stratosphere to get the same effect continuously? And that may not be as easy as it sounds, because if you need a large cooling, you would need to inject a lot of SO2 or precursor gas, and then you start getting coagulation between these particles so that they fall out more rapidly. And so there are all sorts of issues here. It's not easy, or maybe not even possible. But that's what we want to find out. So I will start by, and I guess I've started already, saying a little bit about the principles of climate engineering. And then I will talk a little bit about what we could, just general thoughts on solar radiation management, what it means to cancel CO2 long-wave forcing by reducing solar short-wave forcing. It turns out that that's not a really good cancellation there. And one of the implications is that we get, as a side effect, that we get a weakening of the hydrological cycle. And this is a robust result from many Earth system models. And then the question is, okay, if this happens in the most sort of generic experiment, could there be other ways of doing climate engineering which might avoid this weakening of the hydrological cycle? For instance, if we do something with clouds instead. And then also, how can we understand it? Why does this happen? Can we understand this result from a atmospheric energetics perspective? Okay, first a little bit about the different climate engineering techniques that have been proposed. And this nice cartoon here came out 5 years ago, so it doesn't contain everything, but it contains many of the main ideas that have been proposed. And in red here, I've circled those that deal with what we call solar radiation management, where the idea is to reduce the amount of solar radiation that reaches the Earth's surface and thereby to cool the Earth's climate to counteract the warming by greenhouse gases. So this can be either, like I've already mentioned, in the stratosphere, or it can even be outside the atmosphere by sunshades or mirrors in space. Or it can be in the troposphere, if we can manipulate the clouds so they reflect more solar radiation, or the surface albedo even. And then in blue here we have greenhouse gas removal, which goes beyond the ordinary carbon capture and sequestration. So there's some more vigorous ways of trying to get rid of greenhouse gases. And I'm not going to talk very much about these in this talk, but most of these are, the way it looks now from a current knowledge, this is not an easy solution. This would, of course, be a rather uncontroversial solution compared to some of these, but it turns out they are typically very expensive and not very effective from our current understanding. So it's not, CO2 is not an easy molecule to just scrub from the atmosphere. And then one that is not mentioned here, which Trude, of course, is an expert on, is this one was first proposed by David Mitchell a few years ago. So this is not solar radiation management, because this is long-wave terrestrial radiation management. And the idea is to make the cirrus clouds thinner, the cirrus clouds that have a net warming effect on the Earth's climate, because they trap long-wave radiation. They also reflect some solar radiation, but the long-wave effect tends to dominate by a factor of 2 or so. And the idea is that you would, I'll come back to the microphysics here, but which Trude probably has explained to you before anyway. But the idea is that by seeding by proper material, ice nuclei, you would deplete the cloud. You would get a cloud with fewer and larger ice crystals which would fall out. Okay, so what is actually going on here? Let's just take a broad perspective here on the energy balance of the climate system. So if the climate is stable, it means that the amount of energy coming in and going out is about the same. And that would be, with our current climate, something like 240 watts per meter squared. And we can express this as the solar constant over 4 times 1 minus the Earth's albedo, equal to sigma times the effective radiative temperature to the power of 4. So, and what happens if we double CO2 is that we, and if we now just focus on the effect of CO2 itself and not the temperature change, then we would be reducing the outgoing radiation by 3.7 watts per meter squared. And then the climate system would warm up to get back to that new radiative balance. But if we, instead of letting it warm up, if we try to restore the balance by force, we can use one of these methods here. We can either reduce the incoming solar radiation, that's S, or we can enhance the reflectivity, the alpha, or we can enhance the outgoing long-wave radiation, like in the cirrus cloud thinning. So there are different ways of addressing this equation here. And then, like I said before, there are many disciplines involved when you talk about climate engineering. And so I will mainly talk about this one, climate science. And the questions we ask in climate science about climate engineering is, would it work? And how effective would it be? And what would the side effects be? Of course, we don't know. It may well be that we find, oh yeah, it works. But then the engineers tell us, no, it doesn't, because we can't do it. So that's another aspect we have to consider. Or the philosophers will tell us, no, people will never accept it, so it doesn't matter if it works or not. So all these disciplines have their own veto right, so to speak. Or it could be that we cannot agree on how to handle it, how to regulate it. Like who is responsible if it fails, and how should we regulate it? And also, it could be that, that all this is fine, but it's just too expensive. So we won't do it for that reason. So there are many aspects that need to be considered. And I'm just going to have one more slide on that. And that is on the, should we even do the research on this at all? Like I'm doing. Am I a bad person that I'm doing research on climate engineering? Is that an immoral thing to do? Maybe it is. Maybe it is. And there are some good, bright people that think we shouldn't do this for good reasons. One of the arguments is this so-called moral hazard argument, which means that by doing research on this by climate scientists, we are drawing attention of people around us from emission reductions, because we give them the impression that there's an easy way out. that you don't need to worry about global warming, we're going to fix it. So it's a distraction. And that's a good argument. But one can also argue against that. And I would argue, but I'm happy to discuss it if you disagree with me. I would argue that it's also important that we scientists who don't have an agenda get involved in this research so that it gets done in as neutral and objective way as possible. And then the other argument against the research is the slippery slope argument. That, oh yeah, we scientists, of course, only want the best for mankind, but it could be that other people will take over. The politicians or technology will take our knowledge and use it in a manner that we had not envisaged or recommended. That's also an important argument. And but one can also argue against that by maybe saying that, well, this is sort of assuming that we will find a way to do this, but we don't know that. Maybe our research will do the opposite. Maybe we will find that it doesn't work. I mean, certainly I'm not trying to promote climate engineering, I'm just exploring it. So yeah, these are big questions. Okay, so that was sort of my introduction, and now I will go into the more of the natural science aspects here. And first, just a review of some of these techniques, what they're about, and what are the principles. First, there's mirrors in space, and I think a lot of people consider this one to be quite far-fetched and likely to be very risky and very expensive. But there are people pursuing this, like this Angel guy who had this paper in PNAS a few years ago. And the idea is that at the Lagrangian point in space, where you have sort of balance between the forces, so if you put something there, it will stay. That's what the SOHO satellite is. You could put some reflective mirrors, which would reduce the solar radiation even before it hits the atmosphere. And one of the main model experiments that I will show you in a few minutes is actually based on this idea, not because we think it's a realistic idea, but because it's an easy experiment to make so that we can have a lot of models involved and get a broad ensemble of models. And GeoMIP is the Geoengineering Model into Comparison project. And this particular experiment is called G1. It's sort of the most basic experiment. The way it works is that first you have a control run with your Earth system model. And then at a particular point in time, you simultaneously quadruple the CO2 concentration and reduce the solar constant accordingly so that the radiative forcing, so there's no radiative forcing, no net forcing. So that they cancel each other. And you have to do some iteration. You cannot know in advance exactly how much you need to reduce it. It varies from model to model. So you need some iteration, but you can figure that out, and then you can do the experiment. And you get, so there's basically no net forcing, so there's also then no feedbacks, or greatly suppressed feedback. So it's a nice experiment from that point of view. And then moving into somewhat more maybe realistic ideas. This is, of course, the basic idea that stems from the volcanic eruptions and the one that Paul Crutzen proposed in his 2006 paper in Climatic Change, which sort of has got this debate going on climate engineering. So the idea is to mimic the major volcanic eruptions to somehow get either particles or particle precursors into a stratosphere so that they would form sulfate aerosols, which would then reflect solar radiation. And there are many different methods and injection methods and that have been considered. And so this cartoon here by Alan Ropak illustrates some of that. Balloons, aircraft, rockets, even towers. So we don't know what will be most realistic or efficient if this ever were to be tried. But what we know already from model simulations is there are some well-documented side effects, like stratospheric ozone depletion seems to be an issue. When we finally fix the stratosphere, we're going to start messing around with it again. Also, there are some issues with changes in precipitation, especially if this were not done uniformly over the whole globe. That depends on the how exactly it's deployed. And then if we move into the troposphere, this is another idea that's been around for a while, since 1990, by John Latham. And we know that these low clouds over the subtropics, they have a strong cooling effect on climate because they have a relatively large albedo. They're quite extensive, and they're there all the time, almost. And at the same time, they are, and the surface albedo is very low, whereas the albedo of the cloud is maybe 80%. If you take away the cloud, you have only a 5% albedo, the surface. And the sun is high at these latitudes. At the same time, since they're in the boundary layer, their emission temperature is very high, almost like that of the surface. So they have basically no long wave effect, just the strong negative short wave effect. So this is a strong cooling effect. So if we could somehow make these clouds even more extensive or even more reflective, then and the idea here is to suck up seawater by some vessel here, and then to inject sea spray into the atmosphere, which, when it evaporates, it leaves behind sea salt particles that get sucked into the updrafts and go into the clouds and make the clouds more reflective. Side effects here are not as well known. I mean, this is something that I've been concerned about, that these are relatively small regions we're thinking about, where you would reduce the incoming sunlight tremendously. So I would think that it could disrupt marine ecosystems, but I haven't seen any study of that. So this is just a thought. And then there's so that's about brightening the clouds. How about brightening the surface? And the desert, who cares about the desert? Why don't we just make them a little bit brighter? It seems like an easy target, that make the Sahara Desert covered with some very reflective material. I mean, it's already a wasteland, so what the heck? But the albedo is not very high, actually. So if you could somehow get the albedo to be like that of snow, it would make a huge impact. And there have been some studies of this, and yeah, it has an impact, but there's an undesired side effect that seems to be emerging from these studies, and this figure here illustrates that. Because what happens here when you're imposing this cooling effect over land is that you get sinking motion there. You get sinking motion over land, and then you get the secondary circulation with rising motion of the oceans. So what you're essentially doing is that you're making the desert even more extensive, which is not really what you want, because most people live on land, and we need all the precipitation we can get over low latitude land regions. In that sense, this method here would be better, because it does the opposite. Here you're cooling down the ocean, so you're getting more cloud formation over land. I'll come back to that. Okay, then how about cirrus clouds? And here the idea is to inject efficient ice nuclei into the regions where cirrus clouds form. And these cirrus clouds have a net warming effect, as I've said before. So the idea is that you would force a transition from homogeneous freezing naturally to heterogeneous freezing. And if you inject the right number of ice nuclei, the number that's not too high, then you would get fewer and larger ice crystals and optically thinner clouds, and you would get a stronger outgoing long-wave radiation. And here also the side effects are not well known. People often ask me about this, so I put it up there, toxic effects of bismuth. Maybe Trude has some thoughts on that, I don't know. But a big question is also when, where, and how to inject, and I know that Trude has also looked into that. So this is maybe the most recent and least explored of these four main techniques. Okay, so these are the techniques, and now I'm coming to the question that I'm interested in this talk in particular, and that's the hydrological cycle, not the temperature. We know we can cool down the planet, but what are the side effects associated with that? And one reason why we might expect that there would be side effects is that we see, if we just look at the spatial and temporal patterns of CO2 forcing and solar forcing, they don't match. So if we try to cancel this by that, it's not going to be a clean cancellation. So that's just an indication, it's not so simple. And it turns out that it isn't that simple. And so results from these G1 experiments show that there are systematic changes in the hydrological cycle. And I'm going to just walk you through why that, or how that plays out. First, this is the net radiative flux when we are reducing or quadrupling CO2 by a reduction of solar constant. So globally average, 0. But it's not 0 everywhere. It's actually quite strongly negative in the tropics and positive at high latitudes. So it wouldn't save the Arctic sea ice, but at least it would reduce the warming, of course. So this is the residual warming. So there's residual warming at high latitudes, but actually a cooling at low latitudes. But the point is that most of the evaporation is taking place at low latitudes. So precipitation would be reduced almost everywhere. So we see that we have a lot of red and yellow here. We don't have much blue. So this is really skewed to the negative side, as opposed to the temperature. This is the global average here is 0. The global average here is 0. The global average here is something like minus 5%. And the implication of that is, one way to look at that is through the Bowen ratio, that ratio between sensible and latent heat that we see in a lot of regions. We see an increase in the Bowen ratio indicating a drying of the land regions. There are also other ways to look at this, but qualitatively they show the same thing. And there are some exceptions. Australia actually has a moistening, but a lot of drying over land regions. But of course, we should also keep in mind that 4 times CO2 is not a good idea either. So this is actually even worse in terms of drying of land regions, especially in the subtropics where the desert regions are spreading and becoming larger. Okay, so back to now the global picture. Okay, so what is going on here? So this is now an ensemble of these models that took part in this experiment. So there's one symbol for each model here. And we have temperature change on the y-axis, precipitation change on the x-axis. And this is, so we start with pre-industrial conditions, 1850, and then we do 4 times CO2, and we end up here, so we get warmer and wetter, okay? But then we balance 4 times CO2 by turning down the solar constant, so we get a temperature change which is 0, but as I mentioned before, the precipitation change is not 0. In fact, all the models agree on this. So it can't be just a fluke that there's a badly parameterized hydrology in one of the models. All the models agree on this. So this is a fundamental, or at least a general result among the models. And it turns out that this is actually something that people have been thinking about for a while and have explained. And for instance, there was this paper by Allen Ingram, Nature, 12 years ago, where they were thinking about the same kind of question, but not in terms of climate engineering, but in terms of global warming. And they looked at the climate models at the time and the hydrological cycle. And this is sort of one triangle here for each model. And this is the red line is then an average or best fit of these models. And we see that even for a temperature change of 1.4 degrees, there's no increase in precipitation. And this is the Clausius-Clapeyron line. And this one actually is a good approximation to how the amount of water vapor in the atmosphere changes. But it turns out the precipitation doesn't follow the same rules. Precipitation does not go by Clausius-Clapeyron like humidity does. It goes by some other rule. It has a weaker dependency. And why is that? And if you, of course, this is not what they did, just my thinking here, if you were just to extrapolate it, you would again get something like 5% for a zero temperature change. So let's look at some equations. I'm not going to show you a lot of equations, but we need an equation for the energetics of the atmosphere, energy budget of the atmosphere. And I mean, the way it works is the atmosphere is not an energy, I mean, it's in energy balance, but it's not in radiative balance because there's more than just radiation contributing. In reality, the radiation is systematically a cooling effect, but this is then balanced by release of latent heat and sensible heat from the surface, where latent heat dominates. And we can express this by this equation here. So the change in atmospheric heat content is given by the surface fluxes plus the radiative flux divergence, which is the difference between the net downwelling at top of the atmosphere minus net downwelling at the surface. Okay, so how does this equation help us? And now let's think about perturbing this equation by some change, either climate change or climate engineering, and so we said put deltas then on all the terms here. And then now I've solved the equation for the surface fluxes that I'm interested in. And if we now for a moment think about that the climate hasn't had time to change much as a response to the perturbation, we're looking at sort of the fast response. Let's see, like in the model simulation where we spontaneously increase CO2. But the fluxes have had time to change because that's instantaneous. So the outgoing long-wave radiation is increasing. At the same time, the downwelling long radiation is also increasing. But it turns out that if we're adding more CO2, then this term will be larger than that one. Or that change will be larger than that change. And that's important because it means that, so we're reducing this positive term here, and then we're increasing this one, but much less than we're decreasing this one. And this one is zero. So all in all, we're reducing the latent heat flux if we add more CO2 and keep the temperature constant. And if we reduce the latent heat flux, we're also reducing precipitation. So this is a fundamental property of CO2. The CO2 influences the atmosphere in this manner.
Jon Egill, how fast would that
Yeah,
have to be for this argument to be valid?
Yeah, that's a great question. I mean, in models, this is typically done by keeping the SST constant. What I have done in simulations I will show you is that we look at the first year of the simulation, which turns out that already the first year the temperature is starting to change. So yeah, I guess maybe the first month might be more appropriate, but yeah. But at least first year is maybe an approximation that has been used in the literature, and we are using that. But then, of course, if you then go further in time, then the slow response or the feedbacks will start kicking in, and then that after a while that starts to dominate, and the climate system doesn't care anymore what forcing it was that caused the perturbation. It's just the response, the climate system's own dynamics that determine the nature of the response. And then in a warmer climate, a lot of these terms start changing, but it turns out that the change of this term, outgoing long-wave radiation at the top of the atmosphere, dominates, and that means that you get an increase. You get a positive perturbation, you get an increase in latent heat, you get an increase in precipitation. And then if you add these two together, the fast response and the slow response, you will find that, yeah, if you double or increase CO2, you will get an increase in precipitation, and that's because of the warming effect. But the increase will be smaller than you might think, for instance, compared to another type of forcing, because of this particular way the CO2 has a stronger effect at the top of the atmosphere than at the surface, which again is related to how CO2 is well mixed in the atmosphere and it overlaps with water vapor in such a way that, because most of the water vapor is in the lower troposphere, so that's why the effect of the surface, this effect tends to be rather small, whereas this one tends to be large, because in the stratosphere there's no water vapor, so CO2 has a strong effect there. Okay, so that's sort of some of the principles here. Now let's look at what are the simulations showing us for the hydrological cycle for these different methods. And now I'm going to focus a little bit on these two methods that deal with clouds, I guess because that's closest to my heart. So let's first look at marine cloud brightening. And I mentioned this before, that marine cloud brightening as opposed to land cloud brightening may have this actually favorable side effect, that it may enhance precipitation over land. At least from these kinds of arguments you might expect that. And it turns out that that's sort of true. And this is from a paper we had where we had three models. So the figures I'm showing are averages or results from three Earth system models. And first of all, we're looking here at the change in top of the atmosphere net radiation, where we've brightened all the low marine clouds at low latitudes. And as a result of that, we get these strong negative forcings over the subtropics. But we see that we also get a compensating positive forcing over low latitude land regions. And if we take a look at this along a latitude, if we take a cross section, we see that there's a tendency for, and this is omega here now, so blue is a rising motion anomaly and yellow is a sinking motion anomaly. So we see there tends to be, there are some exceptions, but it tends to be rising perturbation over land and sinking over ocean in many cases, not in all cases, in both hemispheres. We see the weapon of blue over land and yellow over ocean here, which is consistent with that argument I presented. And it turns out that indeed, if we look at the precipitation, and this is now an experiment where we are doing climate engineering on top of an RCP 4.5 scenario. So we're cooling down the climate by about 1 degree. And nevertheless, we see many low latitude land regions with increased precipitation in the blue here, which means that we're really suppressing it a lot over ocean. So there's this shift from ocean to land. So that's an interesting aspect where the marine cloud brightening sort of modifies the simple picture I showed you before, where we just turned down the solar constant and we got this overall reduction in the hydrological cycle. For cirrus cloud thinning, there are also some interesting deviation from that simple picture. And first of all, this is a figure from Trudeau's paper where we're looking at change in cloud cover when you seed the cirrus clouds and make them thinner. So we see that we're depleting the cloud amount here. And then in this paper, we did a much simpler version of this. Trudeau did this very carefully with state-of-the-art, or even more than state-of-the-art cloud physics to simulate as accurately as possible the competition between heterogeneous and homogeneous freezing. In this experiment, we were wondering whether one could just simulate this nice experiment by just manipulating ice crystal fall speeds, which is a very crude way of doing that. But the idea is that if it works, if it gives results similar to this, then that could be a cheap and easy way to get many models involved in studying cirrus cloud thinning. And it seems that that's happening now. People are interested. Because at least if you look at cloud cover, it's similar. So in many ways, even though it shortcuts all the appropriate physics, it may be a good proxy to get more people involved in doing this experiment. So I'm going to show you some more results of that experiment. And so this is the model we were using, Anchor Cam 5 at about 1 degree resolution with slab ocean. And we have a control simulation, and then we have a simulation where we doubled the fall speed, and then we have another one where we doubled it just in certain regions, and then we have one where we did the opposite, where we reduced the fall speed, which would make the cirrus clouds denser instead of thinner. And here, if we look at the thinning minus the thickening experiment, we see that we do get, as desired, we get a strong reduction in long-wave cloud forcing. So, and we do get also a reduction in short-wave cloud forcing, but this effect is much larger. We see the global average here is minus 5.4, here's plus 2.4. So it's definitely a cooling effect on the climate system. And here's the cooling that we achieve in that experiment at the surface with an Arctic amplification, and then here in the troposphere with an upper troposphere maximum. So just the signature of any, like I said before, after you run model for many years, the signatures become independent of the forcing that caused them. But in the beginning, the nature of the forcing is crucial. So, and we've looked at this a little bit more now to understand better what's happening to the hydrological cycle. And as I mentioned in my response to Ron's question, we have assumed that we can use the first year as a proxy for the fast response, where the results are strongly influenced by the nature of the forcing, and then an average of the last 10 years as an indication of the response, the slow response. So now I'm showing the results for the first year, and now I'm going back to the equation I showed you for the energy budget of the atmosphere. So this map is showing you now the flux divergence, the radiative flux divergence, which is a source term in that equation for latent and sensible heat. And red are positive values, and green and blue are negative values. So we see that, and this is when we are thinning the cirrus clouds. So we see we have a lot of red here and not so much green. So we're really cooling the atmosphere. And when we cool the atmosphere needs to compensate for that by getting larger turbulent fluxes from the surface of sensible latent heat. There's also a storage term, because the atmosphere, even although this is the first year, it's already starting to cool. So that's why these numbers don't quite match. But qualitatively, this is a result of that. And then we get a precipitation change, which I'm not showing you, but which is consistent with this number. And if we do the opposite experiment, where we make the cirrus clouds denser, we get exactly the opposite result. We get a negative flux divergence, so we're now warming the atmosphere, and that will lead to a reduction in the turbulent fluxes. If you like to think about it in a different way, you can think about it this way, that you're enhancing the static stability of the lower troposphere. So you get less convection. That's another way to think about it. So you reduce the turbulent fluxes, and you reduce the precipitation. And so that's the first year. That's just to understand the energetics. And then if we let the model run and let the slow feedback start influencing the results, we can look at what that does to the temperature and the latent heat flux. So latent heat flux is a proxy for precipitation. And this is surface temperature. So this is what we just looked at the first year. And then for later years, we start moving along this line here with a lot of scatter, but we're moving in this direction. So the temperature is starting to cool because we're making the cirrus clouds thinner. We're letting a lot of heat out to space. So because of the cooling, precipitation and the hydrological cycle is suppressed. But still, nevertheless, we see that even at 1 degree cooling, we still have a zero change in precipitation compared to the original experiment. And that's because of what we saw here. So the nature of the forcing is important, not only the response.
Are these monthly values?
Yeah. And then this is when we do the opposite, and this is pretty much a mirror image of what we just saw. This is when we make the cirrus cloud denser. And this is the first year that I showed you before, and then we move along this line. And we see that if we look at this dashed line here where it intersects the best fit line, we see that for even for a warming of about 0.7 degrees, there's no increase in latent heat flux. And that's because we're warming the atmosphere by this change of the cirrus clouds. So it's not just the temperature change that is influencing the hydrological cycle. So to summarize, and this relates to what I just showed you, that I hope I've convinced you that different climate engineering techniques cause profoundly different hydrological responses. So we cannot just apply as a general rule the result we found for the simple experiments where we turned on the solar constant. Those results do not necessarily apply to any particular technique because they all have their own inherent effects on the atmosphere, which we can understand from these energetics perspectives. As we saw for solar constant reductions, if you want to maintain a constant temperature, it will inevitably imply a weaker hydrological cycle because of the different sensitivities to solar and CO2 forcings. So this is not just a fluke, this is an inevitable result. For marine cloud brightening, yes, you're also reducing the solar constant, the solar input, but you're only doing it over ocean, so things get a little bit more mixed here, and we get this sort of favorable side effect that there's a tendency for moistening of the low latitude land regions. So side effects are not necessarily a bad thing, but it can be a bad thing, of course. In the case of cirrus cloud thinning, since it operates in a long wave, it avoids the non-cancellation, and it seems that maybe this is a too strong term, but at least according to what I just showed you, it avoids the suppression of the hydrological cycle, which makes it an interesting idea. But of course, we should keep in mind, so we don't get carried away here, that some or even all of these techniques may turn out to be ineffective and or impossible to deploy. So this is currently this is all science fiction, all of these techniques. Thank you.